Welcome back to Science Fantastic with Professor Michio Kaku. You know, several months ago, back in the early days, back in April, in fact, we had Carl Zimmer on the airwaves talking to us about the coronavirus. Well, that was 5 months ago, and it seems like an eternity ago, because back then in the early days, the government was confused about masks. Some doctors said that masks are not necessary and may take away from the masks necessary for first responders. It was simple back then. You had a fever, cough, chest pains, you talked to the doctor, and you quarantined yourself. Boy, have things really changed. So once again, with us today is Carl Zimmer, science journalist, author of a book called She Has Her Mother's Laugh, The Powers, Perseverance, and Potential of Heredity. And he writes for the New York Times, Discover Magazine, National Geographic, and he's written 13 books. And so once again, with us today is Carl Zimmer. So Carl, glad you could be on Science Fantastic.
Thanks for having me.
Well, back then things were rather simple, but now we hear about asymptomatic individuals that seem to defy the usual conventions. So could you explain to us how asymptomatic individuals are a game changer?
Yeah, if you look at other respiratory viruses, let's say like influenza or SARS, which is actually closely related to COVID-19, these viruses are most infectious right around the time that you're showing symptoms. So you develop a fever, bad cough, and so on. That's when the virus is making lots and lots of copies of itself and putting other people around you at risk. And so people kind of assumed that this new coronavirus that causes COVID-19 acted the same way. So people would just sort of keep an eye out for symptoms. You know, people who had a fever, if you isolated them, that would be a good way to control this. And it turns out this is a new virus that plays by new rules. And actually, you can be most infectious actually before you start showing symptoms. So you can go for days carrying the virus around you before you seem sick at all. And there are a substantial number of people, the estimates vary, who end up never showing any symptoms at all. And so what that means is that we have a really hard time controlling the spread of this disease because we can't just look at people and see if they're sick.
So that means that in some sense people are under the radar and can be spreading the virus even though they feel perfectly okay. Is that right?
Yeah, I mean, a lot of the cases of spread have been in places where you wouldn't expect really sick people to be, places like bars and churches and offices. So, yeah, people feel fine. They go about their business, and they can get dozens of people sick at once.
And I've heard that estimates are that up to 50% of people who have the virus could be asymptomatic. And so in schools, when you have thermometers that measure the temperature of children and also customers, you could be missing a huge chunk of people who are actually infected by the virus, right?
Yes. Measuring fever is not a very good way to track sickness and to filter people out. It may help. If someone has if someone's coming into an office building and has a really high fever, you don't want to let them in. But you could be letting in people with no fever at all who are just as infectious.
And I read a report recently where one of the cruise ships, the Diamond Princess, scientists were able to track using computer modeling the spread of the virus. Apparently one person spread the virus to up to 700 individuals on that cruise ship. So this is more than just coughing, right? I mean, it seems that scientists have underestimated how infectious this disease is.
Well, again, this was a new virus, and so scientists used the knowledge they had from other viruses to try to come up with hypotheses for how this new one behaves. And then they were able to start collecting data, and it became clear that this virus was indeed different than they had expected in some ways. this cruise you mentioned was it was kind of like an experiment in a way, an unplanned experiment where you have a whole bunch of people in this contained space, very defined space, and so scientists could really get down into incredible detail about how this virus spread around. They would look at the genes in the viruses to make sure that they knew exactly how viruses were going from person to person by looking at that sort of genetic signature. And so, yes, it turns out that, one person can directly infect dozens of people, and then they can spread it on to other people as well. There's a lot of provocative conclusions they drew. You didn't just have to be like face-to-face with someone to get infected. It's possible that the virus was being spread around in droplets of various sizes, maybe was able to move pretty far distances on this ship. So that's become a real sort of important source of information, not just for cruise outbreaks, but for how we're going to deal with schools and churches and all the rest.
And also there's a big controversy now about aerosols. Most people know that 6 feet is the recommended separation distance for social distancing, but small particles smaller than the average droplet can spread much farther than 6 feet. So what is the latest concerning our understanding of how aerosols, not large droplets, but how aerosols can spread the virus?
There has been a really intense debate going on in the scientific community about how this virus gets around through the air. And it's been fascinating to watch. And it's been very challenging, though, for scientists to come up with really sort of concrete, extensive data about this particular virus. I mean, you can't just round up a bunch of sick people sick with this virus and then, have them cough in front of lasers to track all these droplets and so on. It's hard. And so scientists have been relying on research in the past for other diseases like influenza, where there's been a lot more work done. It does seem that in addition to the large droplets that people may cough or sneeze out and just hit the ground, very fine droplets that you can just release by just talking can spread out in surprisingly high numbers. And, the 6-foot rule that people have given, I mean, it's not like every single droplet hits 6 feet and then drops to the ground. It's a rule of thumb. You're much safer at 6 feet than you're at 3 feet. But honestly, you're actually safer at 10 feet than you are at 6 feet. So, we need to be thinking whenever we look at this new evidence, how good is the evidence? And we should look at it as ways of reducing our risk.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is Carl Zimmer, science journalist, author of the book She Has Her Mother's Laugh. And today we're talking about what we have learned in the last 5 months. 5 months ago we had him on the air, and things seemed so simple. It was a virus that was out of control, but there are simple measures you can take. Well, boy, have we learned a lot in those last 5 months. Well, speaking about aerosols, I read an article where you can actually do a test in your own living room. It's called the perfume test and the garlic test. If you spray perfume in the room, it spreads much farther than 6 feet, and you can tell by simply walking around the room and smelling things. And if you talk to somebody and you can smell the garlic on their breath, chances are you're too close to that individual. So do you think, therefore, with all these studies about aerosols, that the CDC and the WHO may eventually change the recommendation on this 6 feet social distance separation? What are your thoughts?
Well, it's a question of managing risk. So, like, you're going to smell a lot less garlic on someone's breath at 6 feet than you are from 3 feet, and you're going to smell even less at 10 feet. But it also depends where you are. If you are in a small office room with no ventilation in it, you're going to smell that garlic a lot. So whereas if you're outside, the breeze is just going to carry it away. So there are going to be a lot of different factors that not just the CDC, but all of us are going to have to take into account as we manage our risk going forward.
And also, Dr. Anthony Fauci was on the air last week talking about coverings for your eyes, face masks, face coverings that cover the entire face that first responders and emergency workers use. Also, wraparound glasses, anything to protect your eyes from getting infected with the virus. So what are your thoughts? You think these are effective now that some of the senior officials in the government are recommending that people have face shields? What are your thoughts?
Well, as I recall, Fauci was bringing that up as a possibility that would be worth looking into. There isn't any sort of, large-scale trial looking at how likely people get infected in their eyes with the COVID virus wearing glasses or even face shields. They're just, these are kind of things that we have to judge just based on what we know from previous studies on other diseases and so on. But, the basic biology stands up that, viruses can enter into the mucous membranes in your eyes and get into your system. I mean, we know that. And so, it's going to be interesting to see just how effective it's judged for people to wear glasses. Face shields, people have debated about it. It'd be much more social to wear a face shield than a mask, I think, because you could see each other's faces. But on the other hand, there's that sort of border along the edge of a shield where viruses can get in or out. So, we're just going to have to keep updating our systems, trying to find the best way to keep this virus at bay.
Okay, well, 5 months ago when we had you on the airwaves, we were basically helpless. There was no vaccine in sight, and therapeutics. There was big debates about what works and what doesn't work. But now we have accumulated evidence for things that do work. They're not cures, of course, but they do affect the course of the disease. So let's take them one at a time. First of all, we have convalescent antibodies. And some people think we can manufacture them, monoclonal antibodies in unlimited quantities. But what are the therapies involving convalescent antibodies? And the technology actually goes back 100 years.
Yeah, that's right. The basic idea is straightforward enough. Somebody gets sick with a virus, could be COVID-19, could be influenza, and if they recover, what that means is that their immune system made antibodies that could wipe out the virus. And so if you take out their plasma, in other words, you draw some blood from them and you just isolate the plasma, which contains antibodies and other things, if you give that to other patients, theoretically, you might help them to fight the virus. And, this has been used for a number of diseases with what looks like pretty positive results. So now there's a big push on to get plasma from people who have recovered from COVID-19 and give it to people. Now, there are some small studies that have some promising results, but we don't have any evidence from the gold standard kind of research that it actually works. That's a randomized, controlled clinical trial with a lot of people, some people getting placebos and some people not. That's the only way that you know if these things actually work. We don't know if they actually work yet or not, unfortunately. And, a lot of people have decided already that this stuff works, and so they don't want to be in these trials. They just want the plasma. They're not willing to maybe get a placebo in a trial to find out if it works. And I understand people are sick, they're scared and so on, but, we could be just wasting our time with convalescent plasma. We have to find out if it really works.
Okay, and of course, there's only a limited amount of time that a person who has recovered from the virus can donate blood and plasma to create this. Some people think we should use monocloning antibodies, that is, artificially create, using cloning techniques, unlimited quantities of this antibody. So what are your thoughts about scientists who work in that direction of trying to create artificially unlimited quantities of this antibody?
So we were just talking about convalescent plasma, and basically if we take plasma out of someone's body, it contains lots and lots of different antibodies for lots and lots of different diseases. And so only a tiny fraction of them may actually be effective against the virus. So some people have said, well, we should just be using the antibodies that really work against this one virus. And this idea, which as is known as monoclonal antibodies, has been in development since the 1970s. There are dozens of the diseases that it's used for very effectively. It's actually quite established medicine. But what you have to do is you got to find those antibodies, you got to find the best ones, and then you got to make them in huge amounts, and then you have to run randomized clinical trials. And so scientists have found now dozens, maybe even hundreds of antibodies that work really well against the COVID-19 virus, and there are a number of clinical trials going on right now. And we might actually know, maybe in a month, about some of the leading candidates, whether they're effective or not. So these could be real game changers. And really, to me, what the big challenge is like, how are we going to make enough of this stuff? Because, you can encode the gene for an antibody and stick it in bacteria or yeast and then produce them like the way we do a lot of drugs. But, you could potentially need enough drugs for hundreds of millions of people. That's a big challenge, and we're not really up to the challenge yet.
Okay, another drug that's been tried, which was a dark horse but has been getting a lot of attention, is remdesivir. So could you explain to us that even though it does not affect the death rate, it does affect the severity of the impact of the coronavirus?
So remdesivir is a drug that's called an antiviral, which means that it interferes with the virus itself. And in this case, remdesivir was designed as a drug that would get in the way of viruses trying to make copies of themselves. And it was initially tried out on other diseases like Ebola, didn't work. So it kind of sat on the shelf. And then when COVID-19 started, some people said, well, hey, let's try this out. Let's see what we got. And remdesivir turned out in cell cultures to do pretty well against the COVID-19 virus. And so it moved on into clinical trials. And those clinical trials do show that it does have an effect, at least in terms of the amount of time that people need to recover, in terms of how long they're in the hospital, for example. So that was the first antiviral to really show this kind of, clear benefit. It's not a panacea, though. I mean, people take remdesivir and die. So we'll hope there'll be more antivirals coming down the pike.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us on the line is Carl Zimmer. He's the author of 13 great books that I've read, that many of them I've read. She Has Her Mother's Laugh is the latest book. He writes for the New York Times, Discover Magazine, and National Geographic. But when we last left off, we were talking about remdesivir, which was originally used to treat Ebola. And some people are saying that certain vaccines and antivirals that are used against one virus can accidentally be used for other viruses as well. And so isn't it true that therefore people are testing different kinds of antivirals against the coronavirus?
Yes, there are antivirals that are being tested that have been used for the flu or HIV, other diseases, and it's possible that the viruses are similar enough that a drug for one works against the other. And it's also true for vaccines, that it's possible that some people are actually already protected to some extent from COVID because they got a vaccine against another disease when they were children. That's an idea that's still being investigated, but there's some reason to think that's a possibility.
And recently, what's gotten a lot of news is a new steroid called dexamethasone, which actually seems to reduce the death rate. So explain to us how this steroid, which is actually cheap, it only costs about $1 a day, they say, has promised to reduce the death rate. And in fact, a close friend of mine who is a physician had a very bad case of the coronavirus, and he was given dexamethasone, and he swears by it. He says within a matter of hours to days, he felt much better. So tell us a little bit about how steroids can be used in the fight against the coronavirus.
So the United Kingdom launched a number of large-scale trials of different drugs to see if they worked. And it was a really good thing that they did it. They set up randomized clinical trials, the gold standard, to know if things work or not. And one of the things they tried out was dexamethasone. And as you say, it's a steroid. And generally the way it works is it kind of generally sort of dials down your immune system. So your immune system is less overreactive. Because that's a big problem with COVID-19 is your immune system eventually just starts attacking yourself with inflammation. And as you say, they saw really striking results. For people who were in a severe case of COVID-19, it really did help. It helped reduce mortality and so on. And they published those results. However, it's not helpful for people with mild cases or early cases of COVID. In fact, it might be harmful.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is biologist Carl Zimmer. Now, you mentioned that the body sometimes overreacts when it fights off the virus. And in some sense, the virus doesn't actually kill you. In some sense, it's the body mounting an attack against the virus that overreacts and causes organ failure and all sorts of problems. So this is called the cytokine storm. So what has been done to prevent the cytokine storm from overwhelming our body? And you mentioned that dexamethasone has to be used at a certain time. So could you explain?
Yeah, so when the virus gets into our bodies, it actually seems to do a few things to manipulate the immune system, probably as a way for it to evade attack. And so the immune system can be kind of slow to respond, giving the virus a head start. And once the virus gets into our lungs and the immune system starts to catch up, there might be a problem for some people that the immune system response just gets stronger and stronger and stronger, more and more inflammation, and it just runs away. So that in a sense, you are killing yourself rather than the virus killing you. And so scientists are trying to figure out how can we stop these cytokine storms. Turns out dexamethasone is pretty good at it, which is interesting because, as you say, it's cheap and pretty simple. Scientists are looking for more sophisticated ways of interrupting the cytokine storm, blocking certain signals the immune system uses. But so far, the results have not been that encouraging. It seems like dexamethasone is as good as we've got right now.
Yes, and as I pointed out, my good friend took it, and he swears by it. He says that it saved him, that very soon after taking it, he felt much better as a consequence. Well, let me ask you another question about vaccines. The Russians have now announced to the world that they have the vaccine, that they're the first out of the gate. Other people are shaking their heads and saying, well, this is more for publicity than anything else. But what are your thoughts about a vaccine?
Well, the Russians do not know if they have a vaccine that works. They don't. They have not completed the large-scale clinical trial using placebos in a randomized way that would let them know. They have injected, as far as we know, a few dozen people with the vaccine, and those people seem to have responded well in terms of safety. They've made some antibodies. That's nice. But nobody knows if that is enough to protect them from getting sick. So every vaccine expert I've talked to, as well as Tony Fauci, said this was a really the announcement goes way beyond the science, and it could be very risky. It could very well turn out this vaccine doesn't work, and then what are they going to do at that point? There are a number of other vaccine candidates that are being tested, And already 7 of them are actually in phase 3 clinical trials. That's those big placebo-based trials. Some are being done in the United States, some in China, some elsewhere. And so that's the way to actually find out if a vaccine works, not what the Russians have done.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is Carl Zimmer, and we're talking about the coronavirus. You know, we had him on the air about 5 months ago, and it seems like an eternity in the last 5 months as to what we've gone through. But let's now talk about phase 3 trials. Tens of thousands of people are going to be tested with these vaccines that will hopefully reach the market sometime later this year or early next year. So tell us a little bit about how these trials are conducted.
So these large-scale trials only happen after scientists have a lot of evidence already. They will run tests on animals, then they will do small tests on people, say on a few dozen people for starters in a phase 1 trial, just to make sure it's safe and that they're actually making antibodies. Phase 2 trial might be hundreds of people. You start to look at the different doses and see how that affects it. Then you're ready for phase 3. In phase 3, you need thousands or tens of thousands of people. Some of them get the vaccine, some of them get a placebo. And actually the people giving the injections and looking at the data don't know who got what. That way there's no bias built into it. And that will be able to show you, if people who don't get vaccinated get sick more and die more, then that's telling you that this vaccine is effective at preventing disease. And then it can also reveal to you if there are unusual or dangerous side effects along the way. So, we really have to wait for phase 3 clinical trials, not just for vaccines, but for drugs as well. Anecdotes and small trials just are not good enough.
And what do you think about those individuals that have volunteered to first get the vaccine and second to be deliberately infected to see whether this is the acid test, to see whether it really passes? What are your thoughts about these individuals? Is it bravery or foolishness?
It's a complicated issue. This is called a challenge trial, and it's not new. Challenge trials have been done in the past with other diseases. And one of the reasons you want to do this is because, in a regular phase 3 clinical trial of a vaccine, you sort of have to just wait for people to get sick out in the world. And if you happen to run a trial where the epidemic has kind of subsided for a while, you might have to wait a long time before you get significant differences between the two groups. So you actually need many fewer people in a challenge trial. And there, as you say, you vaccinate everybody, maybe a few hundred people, and then you just give them all the virus. And you know that they've all been exposed to the virus. So now you don't need to do this kind of comparison. And that can tell you a lot of things about whether the vaccine works or not. However, it's really questionable whether we should be intentionally giving people COVID. People who are young might say oh, it's fine. It's, young people get over COVID really quickly. We don't know that. We know that some people who are young die from COVID, and there may be long-term effects to the heart, to other parts of the body that we're really just beginning to reckon with, because we've only had this disease for a few months. So, it's possible maybe that challenge trials will be the only way to really get good answers, but we can't enter into that lightly.
Okay, and what about those preliminary reports saying that even if you recovered from the virus, you can get it again a second time? So some people are fearful that maybe these antibodies only work for 3 months or a year, in which case you have to continually get booster shots and continually go back to get other shots. So what are your thoughts? Because the data is still unclear on this question.
It is unclear. And again, this is kind of what you'd expect from a brand new virus. There have been some reports of people who tested positive and seemed to recover and then tested positive again. There are not a lot of those reports. And in fact, if immunity just faded away for everybody, then you'd really expect a very different pattern of this outbreak. And so, there's some question about whether some of those results had to do with the tests themselves and so on. So we can't rule out the possibility that you can get sick again from COVID, which is a really depressing thought. But a lot of the scientists right now, their hypothesis is that, at least for several months, you have good immunity if you get sick. And that bodes well for a vaccine, even if maybe you're going to need to get a booster every now and then. It's better to get vaccinated and get a booster every now and then than to be on a ventilator.
And what are your thoughts about the ethics of the sequence by which people get vaccinated? Doctors would get vaccinated first, I suppose, nurses, first responders, and then maybe the elderly, people with underlying conditions. But do you think there's going to be a scramble to get the vaccine once it is available later this year or early next year? Any thoughts?
Yeah, well, there are 7 billion people on Earth who are all, potential victims of COVID. They all ought to be vaccinated, or at least enough people to make it very hard for the virus to get around and really drive down the rate. And, the drug makers are actually producing these vaccines right now in millions of doses. They're ramping up their industrial production, even though it's possible that some of those vaccines won't work. So there's a big risk being taken on, largely through governments supporting these programs. But they're not going to have 7 billion vaccines in December or March. It'll take a while. Okay.
Well, Carl, we've run out of time, but thank you so much for being on Science Fantastic.
Thank you.
So once again, this is Dr. Michio Kaku for Science Fantastic.